Thank you, everybody, for joining us today to this webinar. As you know, the webinar is on broadband wafer-level characterization of next-generation semiconductors. And our speaker today is Andrei Rumyantsev. He's the Director of RF Technologies at MPI Corporation. Next, Andrei. My name is Ruth Gebru. I am going to be your facilitator. I'm the Eastern Regional Sales Manager at MPI America, and just introduced our speaker. A couple of things for the audience. Please hold your questions and any comments you may have until the end of the presentation. But in the meantime, please feel free to put your questions or any comments you may have in the chat box. All questions will be answered in the order that we receive them after the presentation, and we hope that you enjoy. Thank you.
Hello, my name is Andrei Rumyantsev. I am Director of RF Technologies and I am with MPI Corporation. And today I would like to discuss with you the topic of broadband wafer level characterization of next generation semiconductors, requirements, challenges, and possible solutions. Development cycle of the new semiconductor consumable product consists of multiple steps. At first, the modeling test chip is fabricated on the next generation semiconductor process. This chip includes all possible device types, geometries, and configurations. All these devices must be characterized at all possible operation conditions. And all these need to be done multiple times. Process development and modeling engineers request tons of data to be captured to include statistical deviations of these process parameters into the device model. Device models with all these parameters are collected in the process design kit, PDK for short. Circuit designers use PDK elements to develop the new products like power amplifiers, low loss amplifiers, switches, and so on, and to optimize the design of this product to meet the specification requirements. And all this done in the design stage and using electron design environment. Next, the layout of the product is automatically generated and the product is released to the manufacturing stage. After that, the integrated circuit is manufactured, tested, and packaged. And the final stage, the packaged components are integrated on board and the consumable product is assembled. The wafer-level device characterization is a crucial step in the PDK development of a new process. This is extremely important that device characteristics are measured at the highest possible level of accuracy and that the extracted device model parameters are verified for the entire frequency range of the device operation. Only processing trustable and consistent device data, process development engineers can be confident when offering PDK libraries to their customers, the circuit designers. And only operating with the trustable device models, it becomes possible to develop the product that will meet the product specification from the first silicon run. But why it is so critical to have the first pass silicon? In average, it takes from 6 to 9 months from the defined integrated circuit spec to the time when designers having access to the first silicon can measure the new product and make sure that it meets the specification. If the product failed the design verification measurements, designers have to detour and start from the beginning. And this is a very tough situation with a lot of arguments between designers, process engineers, characterization engineers, and modeling engineers. Often the root cause of this fall is inaccurate models of the PDK. In this case, PDK libraries need to be optimized. That costs not only additional resources, but time. And time is the killer. Keep in mind that the average life cycle of the modern mobile device is just about 1 year. If you fail in the first run, you simply do not have another 6 months to optimize your product. You do not have the second chance. Your competitor will win your customer and you will be out of business. With every next generation of the semiconductor process, the maximum operation frequencies of transistors are being pushed closer to the terahertz frequency range. And for 3.5 semiconductors, device Ft and Fmax already exceed 1 terahertz frequency point a while ago. It becomes very challenging to verify PDK models for devices operating at such wide frequency range. These days, we are observing a continuous increase of the wafer-level device characterization system complexity and frequency range, and at the same time demanding and challenging requirements to the calibration and measurement accuracy, system stability over the long time, and data reproducibility. In modern high-speed digital coherent optical communication systems, digital to analog converters are important function blocks which convert digital signals from digital signal processors to analog signals. In such a system, mixers and power amplifiers are the most important components and must have a bandwidth of 200 GHz or greater. Here's one example of the broadband power amplifier operating at 4 frequency bands, from DC up to 250 GHz, and developed for such a system. One of the main goals that microwave measurement engineers strive for is to enable device measurements up to sub-terahertz frequencies with just a single sweep and with one probe touchdown. Let us have a look on the concrete challenges and details. Why are engineers so eager for a single sweep broadband system? At first, a conventional measurement setup has to be reconfigured for every frequency band. For instance, already 3 reconfigurations are needed to extend the measurement bandwidth from 110 GHz up to 220 GHz. System operator has to change RF probes, frequency converters, and other accessories for every frequency band and reassemble them. After that, RF probes have to be replanarized and the whole setup needs to be recalibrated. All this is extremely time-consuming. Also, with every system changeover, the risk of damaging expensive system components increases exponentially. Data inconsistency and discontinuities between frequency bands are another problems of the wide frequency range device characterization. They are reported in various publications over the last years. Such problems are usually hard to fix as they route to multiple sources, such as different types and different design of the frequency extenders used at each band. Calibration residual errors caused by design specifics of RF probes and calibration methods used. Overall system measurement repeatability at different bands. The PDK model parameter verification and verification of the millimeter wave integrated circuits design become challenging with such data quality. Verification of the device model parameters adds another dimension to this problem. The development of the process design kit requires verification of the device model parameters for several temperatures. That means that we have to measure the same device not only at every frequency band, but also for each temperature point. Device contact pads drastically degrade with every probe touchdown, and thus measurement of the same device under test after several RF probes touchdowns becomes difficult. How can we establish high confidence in the DUT model parameters if it is barely possible to measure the same DUT at all required conditions? One possible solution could be a broadband measurement system that covers a wide frequency range in just a single sweep. A possible realization of a broadband vector network analyzer system has been already introduced at RFTech 94th conference. This system is capable to conduct a single sweep S-parameter measurements in frequency range from 70 kHz up to 226 GHz. And its technical specification is provided up to 220 GHz. The system consists of the base VNA and the frequency extension modules that are incorporated in the frequency multiplier arrays. These arrays are realized on the non-linear transmission line technology. You may refer to the paper from Martins and Roberts for some details and system characteristics. The non-linear transmission line modules offer excellent millimeter wave noise floor receiver sensitivity from -119 to -104 dBm for wide dynamic range performance. This wide dynamic range is an extremely important parameter for us, specifically for wafer-level characterization of modern transistors. Because these devices are extremely small, they are very sensitive to the input power level. And to characterize them accurately and not to overload them, we have to use the input signal level starting from -30 dBm or even smaller. In this case, the system dynamic range becomes very important for us, and wide dynamic range can provide us high measurement accuracy even at the very high frequency ranges. Besides the wide dynamic range, the overall system stability is another critical success factor. So the stable the system, the less recalibration cycles it needs, and the more accurate measurement results can be obtained on this system and on this setup. So on the left hand side, we have reported system stability for the transmission measurements, and this is the delta magnitude of S21 parameter, and this is the delta of magnitude on the phase of the transmission coefficient reported on the right hand side here, measured for the system within 24 hours in a typical laboratory environment. So the stability of the system is outstanding. And now let us have a closer look at the design challenges for broadband RF probes. Engineers have to overcome multiple challenges when designing the RF probes for such a system. The 220 GHz module could have a sort of physical transition from the device under test pads that is integrated with the module circuitry. From the electrical perspective, this is possibly the best option, as it eliminates the physical connection between the RF probe and the module. However, such approach seems to be not practical. The DUT contact pads may have different pitches, like 50 or 75 microns. Also, probe damage happens quite often in laboratory environment. The systems are still operated by humans. Therefore, the device interfacing part should be easy replaceable. This means we need a broadband RF probe. This probe should show minimum possible insertion loss, not to limit the system performance, and at the same time it should be long enough to support integration of the modules with the existing probe station. The probe technology and design of its tips should allow for large number of contact cycles, ensure good contact visibility that is required for high data repeatability and reproducibility. The mechanical connection of the probe with the module is provided by Anritsu proprietary broadband 220 GHz interface. The UG387 flange supports alignment for 0.6 coaxial male-female pin connection. This unique interface provides a direct probe connection, eliminating the need for 0.6 mm threaded connector. This interface has another important advantage. It supports the biasing of the device under test through the module. Therefore, both bias parameters and IV characteristics of the DUT can be measured at one touchdown. The new broadband probe utilizes the unique 3D MEMS Titan probe tip technology that is well established for measurement applications up to 110 GHz. The tip shape of the 3D tip makes it easy to monitor the probe contact point under the microscope, Adjusting this probe to the DUT contact pads is very easy. That is why even inexperienced system operators can accurately reposition the probe on the DUT pads and thus achieve high repeatability of the measurement data. The Titan probe tip were scaled and further optimized for the frequency range up to 220 GHz. The width of the probe contacts was also reduced to 15 micrometers. These are the smallest contacts across all probes with the coplanar-based tips. Such a small tip enables multiple reprobing of the same device and measurements of sub-millimeter wave devices with very small pads. The good tip and contact visibility improves the repeatability and reproducibility of the measurement results and system calibration, what we will demonstrate later. The length of the probe body is shorter than 45 millimeters. It is an optimum trade-off between ease of probe integration on a probe system on one hand and low probe insertion loss required for good system characteristics on the other hand. This graph shows the typical insertion and return loss of a 220 GHz probe, green traces, compared to a conventional G-band waveguide probe, red traces. Both probes are of the same pitch of 50 micron. Probe characteristics are comparable. These ensure cross-comparison data that were previously measured on a traditional system using conventional waveguide probes. When designing the coplanar calibration standards for millimeter wave frequencies, it is important to minimize possible coupling of electromagnetic energy into the higher order propagation modes that can be supported by calibration structures and calibration substrate. Besides of the thickness of substrate dielectric material, the design and layout of standards has to be optimized for the following criteria: minimum possible impact of neighborhood elements, maximum acceptable distance to the substrate edges, location of transmission line in so-called homogeneous environment. These recommendations have been recently developed by the European Metrological and Industrial Research Project Planar-Cal, led by PTB Germany, and they are suggested in the guidelines for design of calibration substrates, including the suppression of parasitic modes for frequencies up to and including 325 GHz. These recommendations were addressed when designing MPI TCS 5100 calibration substrate that we recommend for our system calibration. Some characteristics of the new calibration substrate were already reported at the RFTech 94th conference. I would like to share with you just one result of the 3D electromagnetic simulation experiment. It shows how the design optimization can reduce possible propagation of higher order modes in the calibration environment at 220 GHz. Both substrates are at the same simulation condition and the color scale. This is the worst case scenario observed when measuring the longest transmission line. The RF probes are hidden on this picture. The new calibration substrate shows significantly less coupling of the test element with the neighborhood environment and the smallest magnitude of the higher order modes propagating among the substrate. There are several important aspects that must be kept in mind when integrating the broadband VNA system on a wafer probe station. For instance, integration of Anritsu broadband system on MPI stations includes magnet-based cable stress relief support for system RF and control cable interface. It removes the mechanical stress from the module interface and thus protects the probe contact point. This is essential for repeatable and consistent data. Another key system option is the digital micrometer integrated at the x-axis of the RF positioner. We call this option DX. This option enables easy and quick adjustment of the probe-to-probe distance with 1 micron accuracy and repeatability. This is extremely helpful when operator needs to calibrate the system using the multi-line TRL. So how it works? So the procedure is like that. The first, you adjust the probe-to-probe distance and you measure your through standard. Then you leave the probes in the air and cancel or zero out the digital micrometer. Then you adjust the probe-to-probe distance looking at the digital micrometer to the next delta L value. For instance, for the line 1 is 70 micron, and this is what you set up looking at the digital micrometer screen. Actually, you even do not need to look at the microscope. Once the delta L is adjusted, you move to the next standard and measure it, and so on and so on. So these adjustments, as I've mentioned before, is done with 1 micron accuracy, and actually they are operator independent. So this is absolutely unique as the multi-line TRL repeatability and, what is more important, reproducibility. So the difference between operator to operator can be significantly improved. Now I would like to present selected experimental results that demonstrate the system calibration accuracy, measurement repeatability, and the broadband characteristics of an active device under test. Typical key characteristics of the integrated wafer-level measurement system are contact repeatability for well-matched and mismatched conditions, system drift, repeatability of the LRM, probe conservative calibration method, and the multi-line TRL calibration, where we readjust the probes, the probe-to-probe distance, and typical calibration and measurement errors. Here we have a transmission coefficient of a symmetrical matched 3 dB verification attenuator measured with 3 probe touchdowns A, B, and C. Such reference element is available on TCS calibration substrate. The average attenuation was as expected, and consistency of the data is impressive. As you can see, it is hard to distinguish 3 measurement series from each other. So we look at the vector difference between traces, normalizing the last of 2 of them, the trace B and C, to the first trace, A. And these are the vector differences for S11, that is marked as match, and S21 marked as trans. We observe the maximum vector difference for traces B and C versus the first trace A is of minus 30 dB for the both transmission and reflection parameters. The deep match condition, the trace match, where we measured very small quantities, represents the worst case. Calibration repeatability is an important figure of merit of an integrated measurement test cell. This graph shows typical repeatability of the MTRL calibration calculated from 2 calibration series that were performed within about 30 minutes and by an average scale operator. MTRL repeatability is compared against the sum of the system drift, contact repeatability, and LRM calibration repeatability. The related RFTech 95th paper describes how we calculated these characteristics. The increase in the error-bound spread above 200 GHz is primarily due to degrading signal-to-the-noise ratio. We performed this calibration and measurements at relatively low output power of minus 30 dBm at the flange, and that corresponds to about minus 35 dBm at the probe tip at 220 GHz. Such power level might be needed for characterization of advanced active devices. That is why this measurement was intended to explore boundaries of possible device characterization. Finally, I would like to show you the corrected S11 and S21 parameters of a 6 dB attenuator alongside with the worst-case error bounds previously estimated. The graph displays the magnitude values in a linear scale. These are S11 and S22 parameters from 5 touchdowns. This is barely possible to distinguish these 5 traces from each other, and the consistency of the data is outstanding. And on my last slide, I have measurement results of 4 active devices, 4 transistors corrected with respect of the on-wafer multi-line TRL. On the left-hand side graph, we have S11 and S22 presented in magnitude and dB, and on the right hand side graph we have S21 and S12 presented also in magnitude and dB over the entire frequency range. All parameters are acquired in one signal sweep on the presented system, and consistency of the results is impressive. In particular, if we have a look on the coupling, reverse coupling of a transistor, so S21 parameter, this is usually extremely difficult to measure and extremely difficult to model from the measurement results obtained on the multiple frequency bands. Every modeling engineer will much appreciate such data. This brings me to the end of my presentation. Challenges of PDK and IC design verification at millimeter wave frequency range accelerate development of new measurement instrumentation concepts, probe system and accessories. We discussed a wafer-level system that present one of the possible solutions towards this goal. It can conduct a measurement from 70 kHz up to 220 GHz in just a single sweep. This is crucial for characterizing modern semiconductor devices and integrated circuits. The operating frequencies and performance requirements of millimeter wave applications drastically increased over the last years. We also reviewed system architecture, evaluated measurement and calibration characteristics of such a system. Critical and challenging parameters of the system were discussed as well. The proposed system helps engineers to eliminate a reconfiguration time usually required for multi-band measurements, significantly reduces risk of damaging expensive components, improves consistency of measurement and minimizes uncertainty of broadband on wafer measurements. It addresses the industry need of confident characterization of broadband millimeter wave devices and integrated circuits. Also, I would like to acknowledge the MPI RF engineering team contributed to development of the 220 GHz Titan RF probes.